Today we're going to be looking at how to maximize and minimize this function here, constrained by these two planes here, using the Lagrange multiplier method. So typically we've seen cases where we have one constrained variable, or function I should say. So the typical equation for that is the gradient of f is equal to some lambda multiplier times the gradient of g. But in this case, since we have two surfaces that are being the constraints in this case, we will add a second one on, and I'll say mu times the gradient of h. So now we have an equation set up. The way I like to tackle these problems is kind of define everything. So f of x, y, z is equal to x squared plus y squared plus z squared. We'll say g of x, y, and z is equal to, now in this case it's going to be equal to 0. We're going to make an implicit function, x squared plus y squared minus z squared, which is also equal to 0, and our h, x, y, and z be equal to x minus 2z minus 3 equals 0. So at the end of this, we should be left with 5 different equations to come out with some points that should maximize and minimize this function. So what I like to do is I like to find the gradient of all these different points or surfaces. So for f, it's going to be 2x, 2y, 2z, taking all the partial derivatives of x, y, and z. Now with g, the gradient of g be 2x, 2y, negative 2z. And the gradient of h should be equal to 1, 0, negative 2. So now that we have all our gradients set up, we can actually set up our equation. So the way I like to do this is kind of leave it in the vector form, and then I can read off easily. Alright, sweet. So this line here is just substituting our gradient f, g, and h into these spots just along this equation here. Perfect. So now we're going to just equate all of these. So 2x should equal 2x lambda plus mu, just reading across for each component. 2y should equal 2y lambda plus 0. 2z should equal negative 2z lambda minus 2 mu. So now we have 3 equations. Where did the other 2 come from? Well, the other 2 are just our constraints. So these surfaces here. So x squared plus y squared minus z squared equals 0. And x minus 2z minus 3 equals 0. So now we have 5 different equations set up to try and solve all of these multiply methods, or to solve with the multiply methods, I should say, to maximize and minimize this double cone looking object. So my trick to kind of doing these is kind of looking at like what's kind of the easiest to get at first. Now all of these do seem pretty complicated because some of them have like 3 terms in them, which is just a bit overwhelming. But if we notice this term right here, this one actually only has 2 because mu is actually 0 in this case. So I'm just going to denote this in light blue. 2y equals 2y lambda, and we can just simply solve this by setting it to 0 by doing 2y minus 2y lambda equals 0. So we can pull out a 2y of 1 minus lambda equals 0. So this implies, on a new page, that y equals 0 or lambda equals 1 for this equation here. So now we've already gotten a bit of a start. We know some values. So with these, we can kind of just go and place them into our constraints. So these equations here, and kind of see what we get at. So I'm going to pick this equation here to plug it into. It just seems the most easiest, considering there's no y there. Okay, so x squared plus 0 squared, because that's what we're plugging y into, minus z squared equal to 0. X squared equals z squared. So x will equal plus minus z. Just square rooting both sides, like so, and we get x equals plus minus z. Perfect. So now we have some kind of telltale with what x is equal to. It's not definitive yet. We don't exactly have a numerical value, but we're on the right track. So now using our next constraint, which is this one, we can easily plug in plus minus z into here to get some numbers. So now I'm going to use green. So starting with x equals just plus z. Look at our equation. Z I should say, minus 2z minus 3 equal to 0. Just plugging in to x minus 2z minus 3 equals 0, which means we get z is equal to 3. Now here's a pink. When x is equal to negative z, so we get minus z minus 2z minus 3 equals 0, minus 3z equals 3, so z will be equal to negative 1. So now we know that, underline these for the terms they are, awesome. So now we have some z values. So because we know z is equal to plus minus z, we can actually put these straight back in. So if z equals 3, x equals 3, and if z equals negative 1, x will also equal negative 1. Perfect. Okay. So now we can actually find our points because we know y is equal to 0 during this entire time. So if x is equal to 3, y is equal to 0, and z is equal to 3, and second point with x equal to negative 1, 0, and negative 1.